Okay, so in this video we're going to talk about how to fit a neural network. So as we have seen, a neural network is a complex hierarchical function f of x and w. We have some input x and we have lots of weights and bias w of x and the collection weights w. Let's take an example, even more complicated example. So in the previous example, we talked about one hidden layer with 5 neurons and we have 76 parameters. Let's take a look on another example. Here, again, we have 13 different inputs. We have 2 hidden layers. So in the first hidden layers, or layer number 2, we have 5 neurons here. And in the third layers of the second hidden layers, we have 3 neurons. So in the first layers, again, we have 70 parameters. In this layer, from L2 to L3, in each neuron, we have 5 weights and 1 bias. So in each neuron, we have 6 parameters. We have 3 neurons, so we have 3 times 6. We have 18 parameters in this. And in the final layer, we have 3 weights and 1 bias, so we have 4 parameters. So in total, we have 92 parameters here. So it's a complicated hierarchical nonlinear function we want to fit, and usually we have lots of parameters we want to learn from the data. It's why it makes the neural network so complicated. Okay, and if you look at some earlier literature, so people say, okay, to fit this kind of neural net, it can be fit by simply nonlinearly squared, or if you have you want to specify some distribution of your output, it can be fit by the maximum likelihood if you like, but it will be crazy. So in principle, we have a loss function like this. So this can be a least square function, so it is based on y minus f squared. And for some technical reason, we put a 1/2 in front of it, because when we take the first derivative, you want 2 times 1/2 to become 1. You want to cancel all that 2 in front of it, so no big deal. So we can have some loss function like this, y minus f squared times 1/2, and this can be estimated by a nonlinearly square. Or if you want to specify some distribution of y, you may fill this by maximum likelihood. The problem of this kind of conventional technique is that in practice, although the loss function is convex in f, usually the loss function is not the convex function of w. Remember, your f itself is a complicated hierarchical function of x and w. It's not convex. So to do a nonlinearly square, you take the first derivative, you find the first order condition. You have no idea it is the first of all, take the first derivative will be difficult. And second, even if you are super good at math, I'm talking to a group of smart people, so you guys are very good at math. Even if you can take the first derivative of it, you have no idea it is the global optima or just some local optima, unless you want to check the second derivative here and there. It will be crazy. And nowadays, the estimation is usually by some technique we call the backpropagation. Again, it is not new. So the backpropagation has been around for decades, but nowadays it is what people are doing right now. I'm not saying that you cannot solve the problem by nonlinearly square. In fact, if you have a neural net for only 3 layers, for example, and not many neurons, it may be okay to just do the nonlinear square. However, when you have a more complicated case, people are doing backpropagation right now. So what is the backpropagation? So the backpropagation computes the derivative of L of the loss function with respect to any of the elements of W for a generic pair XY using, note that we are not using some crazy mathematical theory. We are using something everyone have been familiar with since the first year of undergraduates. We are using only the chain rule. Chain rule for the differentiation. And another important thing about the backpropagation is that if we go back one slide, usually we want to minimize the average of our loss function. Okay, so of course you can take the derivative of this whole thing. You take the summation, take the average. However, you can just given any pair or given any pair of x and y, you can take the derivative of this guy. Then you take the average of the derivative. It will be the same if you take the average at first and take the derivative second. Let me say that again. You may first take the average, second take the derivative. Or you may first take the derivative and second take the average. Mathematically, they are the same. They are identical. Practically, take the derivative first and take the average second will be way easier. So that's what we are doing now. So if you have no idea what I'm talking about, that's because I haven't talked about algorithm. I'll talk about algorithm next slide. I'm just talking about some story behind it. So you can given a training generic pair, you can just take individual pairs, take the derivative of it, take the average later. Given any training generic pair x and y, we first make the forward pass through the network, which creates the activation at each of the nodes in each of the layers. We would then like to compute an error term and measures the responsibility of each node for the error in predicting the true output y. So what is it all about? Okay, so in the backpropagation, the idea is like this. For any beginning values of our W, first we need to set up some beginning points. For any beginning points, we plug in our inputs x into the complicated hierarchical models. Then we'll get some prediction. And then we look at the prediction. We look at the error we make. Let's call the error delta. And we say, hey, we made some error here. So there must be something wrong in our beginning values, W. So let's make some adjustment according to the delta. That is the idea of the backpropagation. And we can do it again, and again. So we put our input into the model, make some prediction, compute the error delta, we make some adjustment. And then we can plug in our input x into the model again. You can look at the error made in the second run. We say, hey, in the second run, we are not making such huge error like what we made in the first run, but there are still some errors. So let's make some adjustment again. So we make the second run of the adjustment. Then we can bring our x into the model again, make the third run of the adjustment, we can do it again and again. Intuitively, we can do it until it converges. In practice, we may want to do some other regularization, but that's the technical issue we'll talk about later. So I'm done with the story. Let's take a look at the algorithm. This is our algorithm. Given any pair of x and y, we want to perform a feed-forward pass, computing the activations at each of the layer, including the final layer, the prediction for the output. So, given any beginning value of W, given the current W, we plug in our X, perform something we call feed-forward pass, and we compute all the activations in every layer. And we want to take a look at the error we made. So that's it. What we really want to know is if we change the value of W, how much it will change for the loss function. But we begin with this guy. We begin with the derivative of L with respect to Z, our Newton-Raphson, which by the chain rule will be the derivative of L with respect to A times the derivative of G with respect to Z. This is nothing but the chain rule. Yeah, I'm looking at your face and no, you got so it's very confusing. So let's do it all together. So how do I do it? Okay, let's go to our blackboard, and for simplicity, let's consider the list model with only 3 layers. Let's move this guy to the top of my blackboard. Okay, so we have some loss function y and f. Okay, so our f is our function, which is this guy. This is my function. So okay, we consider a neural network with 3 layers. So that's what we have. Our zk is W0. We consider only 3 layers, so our k is 3. So this is Z3. W2 plus summation L from 1 to P2 times WL2 times AL2. Okay, so and our A3 is G3 of Z3. Just in this case, usually in the final transformation, G3 is nothing but the identity function. But anyway, so we want to take the derivative of L with respect to Z. So that will be the same as first we take the derivative of L with respect to A, and times we take the derivative of A with respect to Z. Makes sense? So this guy is, we take the derivative of L with respect to A times, let's denote it, the derivative of A with respect to Z at G dot 3 of Z3. Yeah, that's what I'm talking about. Okay. So in the final layer. This is our delta LK. For example, if our loss function is nothing but 1/2 times the y minus f squared, the delta LK will be something like this. We take the first derivative of this guy will be minus y minus a times the g dot of z. This is from the final layer. Then let's go back. For layers k from k minus 1, k minus 2 to layer 2 and 4, each node in layer, we can set the delta L lowercase k, which is the first derivative of L with respect to z Lk. Then we derive this term by the chain rule. Why would we like to do the derivative of the loss function with respect to z? What we really want is the derivative, the partial derivative of L with respect to W, our weights, because we want to make adjustment to our weights. But we know that our z is just a linear transformation of the activation and W. So the partial derivative of L to W is the partial derivative of L to Z times the partial derivative of Z to W. So what I want to say is the partial derivative can be written as two parts. The first part is something we call delta. We spend a lot of time working on delta. How about this guy? How about the partial derivative of z with respect to w here? It is nothing but, let's go back for 1, 2, 3, 4. Let's go back to here. If we take the derivative of z with respect to w, it's just a. So this guy is delta, this guy is a. So the first derivative is a times delta. Why are we interested in this guy? Intuitively, that's what we are doing. Let's go back to our blackboard again. So we are talking about a complicated hierarchical function, but I want to make a figure, so I can only make it by one-dimensional, but you know what I'm talking about. So let's say that's what we want to minimize. So this is W. We want to minimize some function like this. Yeah, this figure may be we want to make everything simple, so it's a convex function, but we may know that we may not dealing with convex function, but anyway. Okay, let's want to minimize some function of W. The minimization is here. Say if our current W is here. This is our current W, let's call it W0. This guy is our W star, our optimal. Then we should reduce the value of our W0 here, right? So how do we know we should reduce the value of W? What we are doing is we take the the derivative around here. If the derivative is positive, then we know our current value of W is too large. If our current value is here, then we take the derivative around here, and the derivative is negative, then we know our current value of our W is too small. We should increase the value. That is the intuition. So let's go back to our slide. Or let's look at the algorithm backwardly. We want to know our current value of W is too big or too small. So we want to know the derivative of L with respect to W. But we have a complicated function. So we're using chain rule. We rewrite this partial derivative into two parts. This guy and this guy. The second guy is easy. Z is a linear function of W. So the first derivative is just A. This guy is crazy because our L is still a complicated function. But we know L is a hierarchical model. So what we can do is, first, we compute the derivative in the final layer. And then we do the derivative step by step. Then we can get this guy. The whole thing is called backpropagation. Okay, after we get the partial derivative, the next easy. The matrix vector notation simplify this expression because that the whole thing can be written as this. We have a matrix vector notation like this. Okay. And then what we're doing is something people usually call the gradient descent. The backpropagation algorithm computes the gradient of the loss function as a single generic pairs. And after we get the derivative of n different training pairs, the gradient will be the average. And then we have a current value W. If we have some constant greater than 0, let's call it alpha, we update our W using this formula. W minus alpha times the derivative. If the derivative is positive, then we update our W by W minus something. The W will become smaller. If the derivative is negative, we minus some negative thing, which means that W plus something will make the W bigger. And we do it again and again. Try to figure out what's the optimal value of W. Okay? So let's talk about it one more time. The idea for the backpropagation and gradient descent is, given any initial value of W, we want to know if our W is too big intuitively or too small. Of course, we have not only one W. In our example, we have more than 90 parameters. So some W here may be too big, some may be too small, but you know what I'm talking about. Intuitively, we want to update our W. So what we are doing is, we want to take the derivative or loss function with respect to W. If the derivative is positive, then we update our W by W minus something. If our derivative is negative, we update our W by W plus something. So the key for the updating is we want to get the derivative of this guy. Want to get the derivative. So to get the derivative directly will be hard. So what we are doing is we do it step by step. We want to get the partial derivative, this guy. This can be written as two parts. First part is the derivative with respect to z. Second is we take the partial derivative of z with respect to w. The second guy is easy, it's just A, or activations. The first guy can be hard, so we want to do the first guy step by step from the final layer to all the way back to the first layer. That's the whole idea. Okay, any questions? Okay, yes? Oh, yeah. A student asked an excellent question. So some of you guys may have known something called the Newton method or Newton-Raphson method. It's very similar. But what's the major difference of this? In the Newton algorithm or the Newton-Raphson algorithm, so we are not only make the decision to what's the direction to update our parameter, but also how much should we update it. So usually the size of our step will be determined by the second derivative. That's the Newton-Raphson algorithm. Here we are not doing that. Why? Because can you see? We work so hard to get the first derivative. To get the second derivative for this guy will be crazy. And my second answer to that is, so in the beginning age for the neural network, in the beginning age for the gradient descent and the backpropagation, the alpha is usually some constant, 0.1 for example. But nowadays, people are working on this. People are working on, okay, we may not want to do the second derivative because it will be very hard. But we want to do something better than a constant linear rate. Yeah, so there are several different algorithms working on the alpha here, the learning rate. Yeah, does that answer your question? Okay, thank you very much. Okay, so here's the gradient descent. And nowadays, people usually do something even more, something we call the stochastic gradient descent. Okay, the standard gradient descent, what we are doing is, for each training pair, for each pair of x and y, we compute the derivative, we take the average, then we decide how much we would like to update our W. However, it can be more efficient to process smaller batches at a time. Okay, why this is an issue? In the good old days, when your sample size is not huge, you have hundreds of thousands observations. You compute hundreds of thousands derivatives and take the average. Okay, you can do it. When you have millions or tens of millions or hundreds of millions of observations, if for each updating you need to compute millions or billions derivative and take the average, it'll be crazy. So now people are doing something like this. We are not compute the derivative of all training pairs, all observations each time. Usually first we determine the size of a batch, 300 or 500 for example. We decide a size of batch, then we pick 300. If the batch size is 300, we pick 300 observations out of our data, compute the derivative for those 300 derivatives, take the average, and do an update. And next round, we pick another 300 observations, another batch. The size of batch is something you can determine. Some people prefer to use like hundreds, 300, 500. Some people like to use, the batch size can be any number. the batch size can be 1. You can just take one observation and doing it. And when you have a very complicated model, even batch 1 may take some time. So you can take the batch size can be 1. These batches can be sampled at random or systematically processed. For large data set, when you have millions or billions of observations, to do it batch by batch will be helpful, especially when you have when you're not doing your training, your fitting by one computer, but you are working on it by multiple different computer cores, or even several different computers. It will be efficient. You can say, oh, this core you are dealing with this batch, another core you are dealing with another batch. Yeah, then you can do the parallel computing. And so first, you can decide the size of batch. This is something we call the stochastic gradient descent. Okay, a simple question. That's not the first time we see something we call it stochastic. Means that we are not dealing with all the observations, but we only dealing with part of it. Yeah, Professor Kuan talked about something similar last week. Yeah, do you remember what? Yeah, so what did he say? He was talking about stochastic gradient boosting. Yeah, you're right. So when doing the stochastic gradient boosting, we're not doing all the observations at each run. Usually in the stochastic gradient boosting, we are doing half of the observations. So the batch size will be 1/2 of our observations. And in neural network, we are calling it the stochastic gradient descent. The same reason, we are not dealing with the whole bunch of our observation. We are only dealing with one batch at a time. Another thing is called the approach. The approach of the training means that all n training samples have been used in gradient steps. Okay, let's say, for example, we have 1,000,000 observations, and our batch size is 1,000. So we are doing one batch at a time, 1,000 observations at a time. So it takes 1,000 runs to use all our observations. Yeah. We can make a simple figure like this. So we have a million observations. So the first run we use the first batch will be 1,000 observations. The second run we use the second batch, the second 1,000 observations. The third run we use another batch. So in total, we'll use 1,000 different runs, 1,000 batches. Once we use all of them, it's called an approach. And the number of approaches is something you may like to determine at the beginning. So you may say, okay, in total, we'll like the computer to run 5 runs or 10 runs, then we'll call it a day. An average of the training means that all n training samples have been used in gradient step, irrespectively of how they have been grouped. Okay, that's something we call the stochastic gradient descent. Okay, this is about backpropagation, and later we'll talk about an empirical example. Okay, so now we are going to talk about an empirical example, and we are going to use the example we talk about in the same as when we talk about random forest and gradient boosting. It's called the Boston housing. So we have the data of the median value of housing price of 506 different small towns around Boston, and we have several inputs of those towns. We know the per capita crime rate of that town. We know if it's by the beautiful Charles River or not. We know the full value property tax rate per 10,000 people and so on. And according to those input, we want to make good prediction on the housing price of those towns around Boston. And in this course, we are going to use the package called the neural net in R. So nowadays there are several other popular choices to run a neural net, such as the Keras or PyTorch in Python. Okay, so let's take a look at the R together. So this is my R package. So first we want to load the data which is in the package library, and we use the data frame, we name it just data, it's the Boston. Then we randomly split our sample into two parts, the training set and the testing set. The training set covers 75% of our data. And that's it. Okay, there is something we really want to talk about at this stage. Let's go back to our slides. Not this one, sorry. Usually, in practice, before fitting a neural net, we want to do something called scaling. The scaling of the inputs can have a large effect on the quality of the final solution. Okay, so the reason is similar to lasso or ridge. Remember, when we run lasso or ridge, the first step, before we run everything, we standardize the observations. The same thing. We usually try to scale the input. So standardize to mean 0 and standard deviation 1. And it is important in neural net because another important reason is, remember, when doing the backpropagation, you want to have some initial values. Usually, those initial values are randomly determined. But if our inputs are not well scaled, the initial value can mean a lot of it. You consider different initial value, it may bring you to very different results. So usually we do some standardization, and then it allows us to choose a meaningful range for the random starting weights. Usually it's selected from the uniform distribution between -0.7 to +0.7. So this is what do I do for the scaling. So I will not talk about the detail. You guys have the R scripts. So let's run this part. And of course, we have the data, so we can just feed a linear model using the linear regression. So we regress the median housing price to our inputs and make prediction and see how it works. So here, that's what I do. I use the LN to feed the linear model using our training set, and I bring my estimated coefficient to the testing set, make prediction, and I compute the mean square error of it because I want to have a benchmark for comparison. So by doing the linear regression, so this part, by doing the linear regression in my testing set, the mean square error is 21 point something. Okay, this is the linear regression. Now let's see how neural net work. So first we bring the package neural net, and then this is how it works. Some detail I want to talk about at the beginning is that, okay, so for most command in R, like ln for example, to write down the formula, you just need to write down something like this. So the formula is want to regress the median housing price to other inputs. So it's like this, MEDV, and it's the median housing price. And put everything on the right hand side, so it's a dot. For some technical reason, you can't do that in the neural net command. So you need to set up some R object, which is S formula, which is a formula. Then you paste this guy, our formula here. Yeah, I know this is not the best thing we can do, but that's it. So we can fit a neural net like this. So, and again, to fit a neural net, we need to randomly select some initial values. So here I fix the seed because I want to we have the same result every time. So here's the neural net. It takes some time. Okay, but here it is a simple net. So here you can take a look at my command. So hidden equals to 5, which means that I only want one hidden layer, and the number of the hidden units is 5 in that layer. So let's take a look at our result. So we can use plot to take a look at what we have. So that's what we have. So if you take a look at it closely, you can see. So we have in each neuron, it's a linear transformation of those 13 different inputs. So the weights are, for example, 59.34 something, and for each neuron we have a bias, an intercept, a bias parameter. In this case, here, 0.4 something. So here is a neural net with one hidden layer. And of course, we can do some computation of we can bring our neural net to the prediction and see how the prediction of the mean square error. So that's what we have. And we can compare the mean square error of the neural net and the least square. So remember, in the least square, our prediction mean square error was 21 something, and here is the neural net 13 something. So it's better, and we can consider even more hidden layer. For example, if I change this part to C5 and 3, which means that I want 2 hidden layers, and one has 5 neurons, and other have 3 hidden neurons. So let's run it. So here we go. So then we have 2 hidden layers here. So the first hidden layer has 5 hidden units. The second one has 3, and yeah, that's the figure. And we can also compute the mean square error at this part. So the mean square error will be 8 point something. So yeah. So compared with our benchmark, which is a linear regression, yeah, the neural net has very good prediction compared to the linear regression here. So that's what we have. Okay, so that's the neural net.